That's the slides.
Okay, my name is Jiansheng from ASIPP China. I'm very, very glad to be here. Thanks for the conference committee to invite us to join this conference for celebration. And we are honored to present research activities in ASIPP for supporting of future fusion devices. The talk should be given by the Jiansheng Hu, Professor Jiansheng Hu, who is our deputy director, but it's very pity his visa is delayed, so he cannot come here on time. So I will present this talk on behalf of him. Okay. Let's start with the.
уважаемые техники, у нас не переключается слайд презентации. Посмотрите, пожалуйста.
My talk will be given this three parts. There are two very important projects developed by the ASIPP. Will introduce one by one. And in the third part, I will introduce the international cooperation to all of you. Before I start my talk, I would like to give you a very brief introduction to the ASIPP Institute. The full name is Institute of Plasma Physics, Chinese Academy of Science. It locates at a small island with very nice view. Probably you can say this is the place. This is our machine building, is the top mark. And this institute is founded by the Anhui province in 1978. The mission of ASIPP is to research the fusion energy based on the top-mark approach. Now the institute has 14 divisions and 3 research centers. We have more than 1,500 staffs. At ASIPP, we have a very long history. Now we already have 4 generations of top mark, from very old one, HT6D and HT6M. It's conventional non-superconducting top mark. And thanks for our Russian friends, we get the first superconducting top mark from Khrushchev Institute, and that gave us a new field and opened our eyes to the new technology. After that, we designed and developed the Easter top mark. This is the first full superconducting top mark in the world. This is a non-circle cross-section. This slide shows the fusion research strategy at ASIPP. Now we have the Easter top mark and operating. The mission of the Easter is to research the steady-state operation and related physical plasma physics. And we have another important project, which is CRAFT. The CRAFT is mainly used for the fusion technology test. There are 15 facilities to test some key technology for the fusion and for the fusion demo reactor in the future. Now we are designing a new top-mark machine, which is BEST. The BEST is focused on the DT operation in the future. It will start the plasma operation on 2027. until a longer time. As you know, also China involved in the ITER project a lot. And we are also planning to create our Chinese fusion energy demo reactor, which is CFETR. That is our roadmap in ASIPP. This is the picture shows the ISIPP tokamak. It is proposed in 1996, and the machine is finished to be constructed on 2000 years. The first plasma is opened 2006 year. Now until this year, they are already 130,000 plasma discharged to be operated. For the ISIPP tokamak, we have three important parameters: 1 megampere plasma current, 100 million kilo temperature, and 1,000 seconds pulse length. The scientific goals of the ISIPP is to realize the advanced long-pulse static state operation and provide a scientific basis for the design, construction, and experimental operation of ITER and CFETR. I would say ISIPP is not only belong to China. Actually, now it has been a very open platform for the static high-performance plasma operation. I will give you some information in the end of the talk. We have a lot of collaboration from everywhere. The ISIPP has some special characters. For example, it is a full tungsten diverter with high heat removal capability. At the beginning, the ISIPP diverter is installed with carbon combined with copper diverter. And from 2014, the diverter was replaced by the welded tungsten combined with a copper structure. The upper tungsten diverter has been finished 2015. And we also update the lower tungsten diverter from 2021. And now the tungsten diverter allows the heat removal capability can be improved to the 10 megawatt per square meter. It also has a lot of has very flexible heating and current combination. The total input source power can be 30 megawatts. So the heating system includes the low hybrid wave, ion cyclotron wave, and electron cyclotron wave, also the neutron beam injection. The picture shows the heating system distribution before, and now we have the new update from 2020, and all of the heating system has been updated. And one important information is about the neutral beam injection. We changed the balanced power injection to the cold beam injection. And also, like the low hybrid wave, we use pump antenna. And for the gyrotron, I would say the electro-cyclotron heating system is very important for ISIPP tokamak. And the gyrotron is also from our research country, gave a lot of support on this technology. This is our diagnostic system. Yeah, we have a lot of diagnostic, including the magnetic environment, many coils, and some diagnostic used for the operational monitor, like the visible camera and pressure gauge. And the important temperature and the density profile environment. There are a lot of diagnostic systems here. And this figure shows the distribution of all of the diagnostic Until now, roughly statistic shows probably we have already 80 diagnostic systems, and in recent years, several years, we added 10 new diagnostic systems. Yes, a lot of diagnostic for plasma physics. And for the long pulse operation, the stable plasma control is also very important. So we have some fiber optical current sensor to get accurate measurement, and we developed the low zero drift integrator, and the GPU parallel reconstruction is used to get the plasma equilibrium in real time. And for the okay. Can I go back? Yeah, okay. For the non-pulse operation, the impurity and the density control is also an important issue. So we have the lithium coating technology for the plasma conditioning and cleaning, which will be carried out before the plasma discharge. And during the plasma discharge, we also develop the real-time coating with the lithium and the broad powder injection. The figure shows, you can say, the green light during the plasma. This shows the lithium injection in real time during the plasma discharge. And for the particle control, we have the high pump speed of the vessel crop pump to remove the particle. And also we have developed the SMBI and the pellet injection for plasma filling. The MHD for plasma instability, it's also a big problem for the top-mark operation. So we developed the new classical tier mode control system with ECCD, and for the disruption, we developed the prediction system based on the machine learning, and also for the disruption mitigation, we have the MGI technology and SPI, shuttle pellet injection technology. All of these technologies are used to protect the machine. Another interesting point is the lithium. In Eastern Tokamak, we use the lithium coating before a lot for the plasma discharge, and also we have developed the lithium limiter technology, the flowing lithium limiter technology, to test the character of this material as the plasma material. So now the 4th generation has been finished. And the plasma vacuum area, the airway suppression, impurity, and recycling with this technology has been invested in the plasma experiments. I introduced some technology developed on Institomac. Actually, we use this technology. We also carried out the physical research related with the state operation. In East, we have 6 working groups, include focus on different plasma physics topic, which is also following the ITPA. Probably you're also familiar with this. The topic 1 is for the high confined and high beta scenario development. And also we focus on the transport and confinement. The cool MHD disruption and their control is also another important topic. 3D physics studies is used resonant magnetic perturbation to influence the plasma and get to the plasma response. Also for the H mode study, the pedestal and edge physics has been started. And the plasma interaction between plasma and work with constant diverter is our important topic on East, and as well as the energy particles research is focused more and more. Here I show you some results recently. As I said, Instituta focuses on the static operation. We would like to get long-pulse operation because we use the superconducting tokamak. You can see this figure. It shows the pulse length, the duration extend from the beginning of the plasma until now. Actually, we get the 32 seconds H-mode plasma on 2012, and then we get the 100 seconds operation, and we get 300 operation. In last year, we get the 400 seconds H-mode operation. For this long-pulse operation, the integrated solution of high performance has been explored to achieve high confinement and bootstrap the current fraction to achieve high RF current drive at very high density and to achieve a good cool and age integration. Also for the long-pulse operation, the particle and the heat balance should be controlled very well. So for example, the particle recycling, how to control the LMA and mitigate the impact on the first work and the direct heat exhaust should be controlled very well. So now we after this many years experience, I would say all of these results demonstrate our capability of engineering and technical issue for the long-pulse operation on East. Here I show you the new record last year we achieved. That is the 403 seconds reproducible H-mode operation. You can say the time traces of the plasma parameters on the right. This is a full non-inductive plasma operation with the density, Curie-Watt density fraction is about 0.7. And the bootstrap current fraction is larger than 50% by the RF heating injection with zero torque. It's very low torque injection. And the confinement is about 1.35. And we find that there is a strong ITB, which is dominated by the electron heating. And also for the particle exhaust and the heat load, we use we achieved by the cooling constant diameter. And during this plasma discharge, the air gate is very small, and so we get very good cool and age integration performance. Another important result recently is we achieved this solvent plasma discharge with super I mode. Super I mode, probably you know, I'm not sure, it's different from H mode, it's different from L mode. It's between on the, you can see the figure in the middle, there's no pedestal on the density profile, but there's a pedestal on the electron temperature, on the age. And also it's very interesting what we call it super I mode because it is I mode combined with the ITB dominated by the electron heating. So from the electron temperature profile, we can see there's a strong ITB in the core. Here I list all of the parameters. And by this experiment, we find this is very interesting self-organizing regime. A good interaction between energy, turbulence, and heat transport, so that the stational ITB can be sustained during the long-pulse operation. And this result has also been published on the journal last year. Okay, actually there are a lot of physical results, but I will not repeat too much details. I would like to know in the future, in the recent years, there are still many key physical issues like plasma current, drive and profile control, and energy particle physics, and confinement and transport for the ITB in the hybrid plasma, and the plasma boundary interaction with the material core. Now we have also several parameters targets. You can say on the right, we would like to achieve very high normalized key parameters exist or beyond the interlevel. And also we are doing we are pushing the high ion temperature plasma. And also we will also continue the high mode scenario development. And you know, this is a full constant machine. So in recent years, we will still continue the non-pulse operation without the diesel coding. We will focus on the metal impact. The second important project on ASIPP is CRAFT. CRAFT, the full name is Comprehensive Research Facility for Fusion Technology. So you can say this is mainly for to start the fusion demo level key technology. Through this project, it is expected to establish the method and the standard for the manufacture the key material, the component and system for Chinese fusion energy demo reactors, test reactors. This project duration is 5 years. And the facility mainly consists of two systems. One is the large complex superconducting magnetic system. Another one is the diverter system and very extreme condition. Here shows all of the subsystem has been developed based on this project, like the superconducting material conductor testing and high temperature superconducting coil and magnetic. And also we will develop many heating system for the dynamo, and we developed the large linear plasma testing facility. And I will give you some detailed information. Here it shows the large-scale magnetic performance research facility. This facility is developed in order to master scientific and intrinsic physical properties and service behavior of the material for superconducting magnet in complex and extreme environment. And it is expected to carry out some engineering application research as well as. I say this is a large, very large scale. You can see the length is very large, 25 centimeters for one magnet. And the heat on the magnet is 100 kiloampere. Here, this is a high temperature superconducting coil development. We developed the automatic cabling machine, and now the maximum field can be achieved about 21 Tesla. And the operating current can be 6.5 kiloampere for each coil. And here you can see these are our magnet development and test. So now the recent test result shows the magnetic current can be 47 kiloampere. Of course, at the normal 4.2 kiloampere against stable operation. But as I know, this is very large scale and very high temperature, high parameters has been not say somewhere else. This is very good results for such large scales. For the current facility, there's another plasma device. It's a linear plasma device. It is this figure shows the construction of the linear plasma device, including the chamber, diagnostic, magnetic, and it is mainly used for the diverter test and for some the other plasma application investigate. And now this linear plasma facility has got the stable plasma operation until about 25 hours. The plasma can be helium, argon, or deuterium plasma. Another facility is for the diverter and blanket test. The figure shows we use the electron beam guns to provide the high energy plasma to test the diverter and the blanket facility. So by using this facility, the diverter payload can be 20 megawatts per square meter. And the diverter is water cooling. And also the blanket will be tested in this facility. This figure shows our first 1/8 vacuum vessel. You can see it is very large, 11 meter, and it's in the hall. It's much bigger than the people. So it's very amazing to see this vacuum vessel. And this assembly accurate. Now we can achieve smaller than 1 millimeter, and the building weight can be 190 meter. And the surface deviation is 8 millimeter. And the right figure shows our gas reading machine device and technology for this vacuum vessel. Another interesting system is for the remote handling. In the future fusion reactor, you should maintain the machine, and how should you do it in a very hot environment, radiation environment. That is our new developed technology, remote handling. You do not do this work by the human. You can use by the robot. This machine device or arm, yes, this arm is 10 liters, and the total weight is 2.5 tons. Okay, this is our craft project and our EAST project. For the ASIPP, I would say now ASIPP has created a very wide work collaboration network. You can see the figure now. We have established a collaboration relation with more than 120 key fusion research institutes, and it covers more than 50 countries and regions. We get a lot of scientific recognition by our national government. You can see that this international expert is was awarded by our government with the international collaboration prize or some kind of friendship to thanks for this help. And I would mention there are two Russian experts from Russia. One is Velikov and another is Tuminikov. They give us a lot of help, and the Chinese government, Anhui province government, give thanks for this help and give the awards. Also now we get very strong financial support from CAS, with the Chinese Academic Science, and from Anhui Province, from Hefei City. You can say only in these last 2 years, we have 34 international experts benefit from those programs. Like the Pi 5, it's present international fellowship. In active, we have more than 5,000 international experts is supported by this project to visit China, to join us the work, and also we have this ANSO project. By this project, every foreign expert are invited to China, and you can work there and you will be paid by the government. Last year, there's a new pilot program. It's open. It's for the innovation. You can see the left picture. So we call it "We are one." We are one in the world. So we are one in the group, in the fusion group. As I said, ASIPP is a very open platform, not only for China but also for the world. In ASIPP tokamak, you can say in recent 5 years, the joint experiment proposal from the international research has been increased a lot. Now we have about 40% experiment proposal from everywhere. ITER, J, and MIT, UCLA, Russia will be considered in our next step. And we have 3 shift joint experiments for different time zones. So I would say welcome to join this experiment if you have time, and if you like, we are always warmly welcome to any collaboration. Okay, as a summary, I give very fast points. ASIPP focuses on discovering the energy source for the humanity using East, Craft, Fast, CNPR facility as our future roadmap. ASIPP robust efforts and steady operation always support each progress and future fusion reactor performance. Committed to openness and sharing, ASIPP will deepen collaboration with global fusion community. So, welcome to join us. Thanks. That's all of my talk. Thank you.
Thank you.